pick the wrong vessel method for your water depth, and you don't just get a slightly worse or slower installation, you get a pipe that buckles under its own bending stress before it ever even touches the seabed. Vessel selection isn't just some logistical scheduling decision, it's a fundamental, high-stakes structural one. Welcome back, everyone. In today's Explainer, we are diving deep into an absolute mammoth of an engineering challenge, subsea pipeline installation, and why depth dictates exactly which methods you're actually allowed to use.
And that brings us to the brutal reality of marine installation. The stakes here are incredibly high. We're talking about safely transporting millions of pounds of steel pipe from the surface of a rocking ocean all the way down to the seabed. If you get this wrong, it's not just a minor hiccup, it's catastrophic failure.
So, to break down how engineers actually solve this, we'll quickly run through the fundamental physics of the pipe laying problem, explore the three primary vessel solutions, S-lay, J-lay, and relay, and then wrap up by looking at a fascinating structural quirk called the paperclip effect, plus how all this dictates real-world route strategy. All right, let's jump right into the core issue here, the pipe laying problem itself. In really plain terms, marine installation is just the process of physically placing subsea hardware onto the seabed without exceeding the material's allowable stress. And the underlying mechanism you have to manage across all pipe laying is the catenary curve. That's the natural curve the pipeline forms when it's just hanging there, suspended between the installation vessel and the touchdown point on the seafloor. Because you see, a pipe under tension behaves completely differently depending on how it's suspended. Depth fundamentally changes the shape of this curve, and therefore it changes the stress at every single point along it. The main job is getting the product down safely. You are constantly playing this intense balancing act between the massive top tension required to hold the pipe at the surface and the severe bending stress at the bottom where it actually touches the seabed. And to make things even more complex, high-pressure subsea pipelines require incredibly thick walls to resist both internal fluid pressure and the crushing external hydrostatic pressure of the ocean. That thickness entirely alters the pipe's weight and stiffness, which complicates the stress profile even more. Which brings us to our first tool in the toolbox. S-lay, often called the shallow workhorse. Picture a massive, broad vessel deck acting essentially like a floating factory. The pipe joint assembly line is right there, horizontally on the main deck. Sections of pipe are welded, inspected, and coated in a continuous line. Then, the pipe is pushed off the back of the vessel really fast, letting it curve into a natural S shape as it falls. To control the pipe as it leaves the deck, the vessel uses a long, sloping structure over the stern called a stinger, fitted with rollers to manage the overbend. Because that assembly line is horizontal, this method delivers a phenomenal production rate. But physics always demands a trade-off, right? While S-lay is incredibly fast, pushing its depth limits is dangerous. As the water gets deeper, the suspended length of the pipe gets heavier. The vessel has to pull way harder to maintain tension, which generates massive bending stress in both the overbend at the stinger and the sag bend near the seabed. Push it too deep, and that bending stress exceeds safe limits, practically folding the pipe like a drinking straw. So, what happens when the water is just too deep for an S-lay? You bring in the J-lay. J-lay completely flips the assembly line on its head. When the water gets too deep for a stinger to safely support the pipe, you use a massive elevated tower instead of a horizontal deck factory. It lowers the pipe almost straight down at a near vertical angle, usually between 60 and 87 degrees. By dropping it basically straight down, you have no overbend curvature at the surface, which completely eliminates the need for a stinger. This orientation minimizes bending stress and top tension. But because you're using a single welding station and a tower, you're trading that blistering S-lay speed for a dramatically safer stress profile. Just to give you an idea of the sheer scale we are talking about here, 10,000 feet. A highly capable J-lay vessel can safely run pipe past 10,000 feet deep. That is almost 2 miles straight down into the abyss, hanging thousands of tons of steel pipe off a single tower while keeping tensions carefully managed within the pipe's yield limits. It's absolutely wild engineering. Next up, our third method, relay, or the giant spool. Now, what if you want high speed, but you really don't want to do all that welding out on the open, rocking ocean? Relay is exactly what it sounds like. Huge lengths of pipe are pre-welded onshore in a totally controlled facility, which maximizes quality control. Then, they literally spool it onto a massive drum onboard the vessel, like thread on a spool. When the ship gets offshore, the pipe is just unspooled and run through a special straightening ramp. Because you were simply unwinding it, relay boasts the fastest offshore installation rate of all three methods. There is a massive catch, though.
You can't just spool any pipe you want. Relay is strictly restricted to smaller pipe diameters, typically under 16 inches. Why? Because winding heavy steel pipe around a drum causes severe plastic deformation. The metal physically yields. So the diameter and wall thickness limits are incredibly strict because that steel has to survive being permanently deformed and then mechanically straightened back out.
So, looking at our subsea toolbox side by side, it's clear how physics and depth dictate the right vessel. S-lay is your high-speed, shallow-to-deep option, limited by bending stress. J-lay is ultra-deep water, treating speed and cost for safety. And reel-lay gives you lightning-fast offshore installation for medium depths, but only if your pipe is small enough to handle being spooled.
And that specific limitation on relay brings us to something really fascinating. Let's talk about the paperclip effect. Here's what a lot of people miss. Every relay project is managing accumulated plastic strain, not just the final installed stress. The pipe has already been bent and straightened before it ever touches the water. This severe mechanical handling drastically alters the pipe's structural integrity before its operational life has even begun. Think of it literally like a standard metal paperclip. If you bend a paperclip slightly just once, it springs back fine. No lost structural integrity. But if you bend it, then unbend it to straighten it, and then apply a load to it, you are spending down the material's fatigue life. In relay, the pipe yields as it's spooled on, yields again as it's straightened, and then hangs under immense ocean tension. Because of all that intense bending, engineers have a hard limit. They generally cap allowable accumulated plastic strain at just 2%. If the pipe strains more than 2% during this aggressive spooling process, you've run a massive risk of unstable fractures or plastic collapse. The steel just gets too tired to safely hold back the ocean's pressure. All right, wrapping up with route strategy and economics. Now that we understand these physical limits, let's put you in the producer's seat with a quick check. Imagine you have a single pipeline route that starts on a shallow shelf in just 200 feet of water, but travels all the way down an escarpment to 6,000 feet of water. What would you expect the installation strategy to look like? Would you use an S-lay for the shallows and swap to a J-lay for the deep? You might think you'd swap vessels, but the answer is almost always a single J-lay capable vessel for the entire route, even in the 200-foot shallow sections. While J-lay is absolutely an ultra-deep water specialist, it can still technically operate in shallower waters. It just does it at a much lower production rate than a dedicated S-lay would. And the reason for this boils down to cold, hard economics. Remobilizing a second vessel mid-route to switch lay methods is astronomically expensive. Bringing in two massive, specialized offshore vessels introduces tremendous schedule risks, weather delays, and mobilization costs that will utterly destroy a budget. You have to cater to the most extreme depth requirement of your route. Economics and physics are permanently intertwined. So I want to leave you with this provocative thought. Never, ever select a lay method purely based on a cheaper vessel day rate. A cheaper S-lay vessel pushed past its safe depth range risks total catastrophic pipe buckle failure. Retrieving buckled pipe from the bottom of the ocean is infinitely more expensive than simply paying the day rate premium for the right vessel in the first place. In subsea engineering, physics will always overrule scheduling logistics. So the next time you hear about an offshore mega project being heavily delayed, you really have to ask yourself, are they fighting the schedule or are they fighting physics? Thanks so much for joining me on this explainer, and I'll catch you on the next one.